Hello. Now, the bulk of this course is going to be about exploring multiple linear models and doing multiple linear regression. And it's actually pretty short to introduce what, in general this model is. But as you'll see for the rest of the course, we're going to be sort of exploring many different iterations of this same model. It can take many different forms, but the simple model that means is very, very powerful. Okay, so let's jump into it. The multiple linear model is designed to help us answer a certain type of question. And that question is, how does the response depend or is linear related to one variable after controlling for several other variables? So this is going to be about sort of isolating the effect of one of the variables after controlling for other variables, or another way to say it is while holding other variables constant. So let's introduce the notation for the data and the model, and then we'll see why this particular model has that interpretation. So the data, as before, this is what we'll call the response, lowercase y1 up to lowercase yn. Remember, these are just numbers that you can put on your computer. And to introduce it first, we're going to have just two covariates. So covariate 1, the notation is going to be x11, x21, x31, xn1. So what this means is that the first, it's going to have two subscripts. The first subscript tells us which response it corresponds to. So x31 corresponds to the response y3. And then the second subscript tells us which covariate we're talking about. So if we go to covariate number 2, the first one is x12. Second one is x22, x32, up to xn2. So all I have to say about that is just try to memorize which one goes with which, and then you'll be fine. Now here's the model. Remember, this is a model for the response, so we're going to use a random variable, and we're going to call it capital YI, and it's set equal to b0 plus b1 xi1 plus b2 xi2 plus epsilon I. Now, if you're having trouble with the subscripts, maybe just memorize the model formula, and then it may be easier to remember that the I always goes first. The assumption on the epsilons is that they're independent normal 0 sigma squared. Okay, so now let's go into how we interpret the parameters in the model. The parameters in this model are going to be the B0, B1, B2. We're thinking of these as plain old numbers, but that we don't know what they are. So these are not random quantities. And then the last parameter is, of course, the variance of the error term, sigma squared. And our strategy for generating interpretations of these parameters, especially the mean parameters, B0, B1, B2, is we're going to play with the values of the covariates and pick them so that we can isolate individual parameters. So if we look at expectation of y1, that's going to be b0 plus b1 x11 plus b2 x12. And if we take x11 and x12 and set them equal to 0, the formula becomes this. So expected value of yi is b0 plus b1 times 0 plus b2 times 0, which of course is just b0. So we've successfully isolated this b0 parameter, also called an intercept parameter, by picking specific values of the covariates, which allows us to interpret this. And the interpretation is the following. This is the expected response when both covariates are 0. Okay, that one's not too complicated. It's sort of like an intercept. All right, now let's move on to B1 and B2. And to do this, we're going to have to be a little bit tricky here. So here's what we're going to do. X21 is 4, X22 is 7, X31 is 5, X32 is 7. So telling you what these are. So this is the first covariate for the second subject is 4, second covariate, second subject is 7, first covariate for the third subject is 5, second covariate for the third subject is 7. So what we're going to do is, instead of looking at individual values of expected values, we're going to look at differences in expected values. This is going to be a common tactic for generating interpretations of parameters. So let's look at this difference. So the third subject expected value minus the second subject expected value. Okay, here's the third subject expected value. B0 plus B1 times 5, that's the first covariate for the third subject, plus B2 times 7, which is this number, minus B0, now we're working on expected value Y2, it's minus B0 minus B1 times 4, which is that number, minus B2 times 7. And then if we look at this, a bunch of things cancel out, so B0 and B0, B2 times 7 and B2 times 7, and then you have B1 times 5 minus B1 times 4, which is just B1. Okay, so we've succeeded in isolating B1, and now we have to go back and try to interpret what this parameter means. So it's going to be interpreted as a difference in expected values, and it's between two subjects that differ in x11 by 1. So these are the covariates for the first subject. These are the covariates for the second subject. They differ in the first covariate by 1, but they have the same value of the second covariate. So let me just repeat that. This B1 is interpreted as the difference in expected value between two subjects that differ in x11 by 1 and have the same xi2. All right, so that gets back to our interpretation of B1 as the effect of the first covariate while holding the second covariate constant. So we varied the first covariate by 1, and we held the second covariate constant. So that's precisely why in multiple linear regression, the coefficients have that interpretation. It's the effect of the first covariate while controlling for the second covariate, or holding the second covariate constant. All right, now let's do the same thing. This one should go a lot faster because it's sort of analogous to the first one. What we're going to do here is we're going to hold the first covariate constant, and we're going to change the second covariate. So if we go through all the math, it's B0 plus B1 times 4 because of this, plus B2 times 4 because of this 4, plus B2 times 8 because of this, minus B0 minus B1 times 4, minus B2 times 7 is just B2. So what we've done here is we've set this up so we have two subjects whose first covariate is the same, and then whose second covariate differs by 1. And if we do that, we can isolate B2, which means that B2 is interpreted as the difference in expected value between two subjects that have the same xi1 but differ in xi2 by 1. And therefore it means it's the effect of the changing the second covariate while holding the first covariate constant. We can interpret these B1 and B2 as slopes as well. So it's kind of like it's the amount that the expected value changed per unit change in the covariate. And again, remember, it's while holding the other covariate constant. Now the last parameter is the variance parameter. This has the same interpretation before. So sigma is going to be interpreted as the expected amount that the response deviates from its expected value. So it's sort of the difference, average size of the difference between the actual response and its expected value. So of course, when we collect data, we're going to expect to get a certain value, but what we actually observe is going to be different, and the size of that difference is measured by sigma or sigma squared. So that was the model with two covariates. It's very easy to sort of just tack on additional covariates. So in general, we're going to have p covariates. I don't know why, but p seems to be the standard letter to use for the number of covariates. So we're going to have p covariates for the ith subject. Those are going to be labeled xi1, xi2, up to xip. And then the model is the following. There's several different equivalent ways to write it. One is to say b0 plus b1 xi1 plus ... plus bp xip plus epsilon I. Same assumption is about the epsilons. We can also, instead of using this ... thing, we can use summation notation, which is a bit more explicit. Say b0 is sum j equals 1 to p, bj xij plus epsilon I. Another common way to write it is to just start the sum at 0. So this will include b0. But then you have to define xi0 to be 1. So if you define xi0 to be 1, you're going to get b0 times 1, which is the same as this, plus the sum j equals 1 to p bj xij. So those are the same. And then we can write it sort of directly in terms of the distribution, which is the following. And all these ways are equivalent. So you may see in papers or books or articles that there's different ways of expressing this model, and these are all equivalent. Now, what is the model degrees of freedom? Now, assuming there's no funny business going on, like one covariate is sort of the same as another covariate, just expressed in different units, so we have a bunch of distinct covariates, the model degrees of freedom is going to be p plus 1. So even though they're p covariates, the model degrees of freedom is p plus 1, and that's because in addition to these p regression coefficients, we have the intercept b0. So if you were to count these up, you get p plus 1. So that's the model degrees of freedom. To generate estimates for the regression coefficients, we use the residual sum of squares criterion. Just a bit of notation to make this easier. We're not going to do matrix vector algebra, but the notation of vectors is going to be really useful to us. If I say b with a little line under it, and then I define it this way, this means this is sort of a mathematical object, a list of numbers that holds all of the regression coefficients. So this is just this b with a line under it. The vector b is a object that just lists out all the covariates. This is just think of this as a notational trick so that we don't have to write out b0 up to bp. So if we do RSSB star, that's the same thing with stars added here. This is the residual sum of squares criterion, and it has this definition. So it's always going to be the response minus something, and the thing you're subtracting off is the expected value, but you're plugging in a candidate for the regression coefficients. So if you look at that is this formula up here, and then you square it. So this is the residual sum of squares for a candidate B star. And then the particular B that we're going to choose as our estimate of the regression coefficients is the minimizer of this thing. Now before, when we did the model with no covariates and we did the model with one covariate, we were able to write down relatively simple formulas for what the minimizers of the residual sum of squares criterion were. All I'll say about this in this case is that in the multiple linear regression case, which is kind of the more general case with p covariates, there is a formula for the vector of regression coefficients. But that formula involves vectors and matrices and matrix vector multiplication and matrix inverses, which is not something that you would not be able to understand. I'm sure you could get it, but it would take a long time for us to sort of introduce all of the notation and the conventions for multiplying matrices and taking inverses that it's better just to say that there's a formula. If you want to go into the details, and I think you could handle this, is the class to take at Cornell would be BTRY 4030 or 5030. So we'll just say there's a formula. It's complicated, and we'll just leave it at that. Now the formula for the estimate of the variance parameter is going to be the same as we had before. So what we do is we take the residual sum of squares evaluated at the minimizer, and then we divide by something. And the thing that we divide by is the residual degrees of freedom, which is simply n minus the model degrees of freedom. So you'll see me write this two different ways. So here I'm writing it n as n minus the quantity p plus 1, which is, and I've deliberately written it different here because you'll see it both ways. This is n minus p minus 1. So it's RSS b hat over n minus p minus 1. It's not correct to say n minus p plus 1. It is correct to say n minus the quantity p plus 1. And again, there's nothing new here. This is simply, I take the residual sum of squares, evaluate it at the minimizer, and I divide it by the residual degrees of freedom, and that gives us our estimate of the variance parameter. Now, if we want to do testing, the first thing we have to figure out is what are the sampling distributions of our estimators. So the notation we're going to use is big B hat J is the random variable version of the estimates. So just to go back here, I said that B hat there is a formula for B hat involving matrices. It also obviously involves the responses Y. So this little b hat is going to be the particular formula where you plug in the data little y. And this big B hat, again, is just the same formula, but we're going to plug in the model, namely the random variable capital Yi. So this is the random version of little b sub j hat. The distribution is normal. The first thing we'll say is that the expected value of this normal distribution is the thing it's trying to estimate, little b sub j, which means that this estimator of the regression coefficient is unbiased. So the least squares estimate, or least squares estimator of the regression coefficient is unbiased. Okay, that's good. The other quantity we have to work out when we say something has a normal distribution is the variance. All I'll say about that is that the variance of this thing has a complicated formula. It depends on sigma squared. Does not depend on the responses though. So this just depends on sigma squared. Okay, so putting that together, we say that big B hat J has a normal distribution. It's unbiased, meaning that its expected value is the thing we're trying to estimate, little b sub j. And there is a formula for the variance that I'm not giving you here. Just to continue with this notation, the standard error is simply the square root of that variance. So this is, like I said, this has a formula and it depends on sigma squared. So this is standard error. I use the square root of the variance and I use the formula that involves sigma squared. If I put a hat on the SE, that means I'm using the same exact formula, but I'm plugging in the estimate of sigma squared. And then this is the random variable version of that, which means I'm plugging in the random variable version of sigma hat squared. So this is just so we can remind us of the notation and we can keep it straight. All right, now let's go to testing. The testing works basically exactly the same way it did in simple linear regression. So if you want to test a hypothesis such as b sub j equals 3.2, we construct the t-statistic, b hat j, this is our estimate of the jth regression coefficient, subtract off its hypothesized value, and divide by the standard error, sort of the sample standard error. So this again is going to be a number. This is something we can calculate in R. This is something we can calculate in R. In this class, we're just going to use the LM function to give us these numbers, but this is something we can get. And we're going to compare this statistic, which is a number, to the distribution corresponding to the random variable version of that statistic. So we're plugging in big B hat J here, minus 3.2, and divide by the random version of the standard error. And it turns out that this thing also has a t-distribution, and the degrees of freedom is the residual degrees of freedom, n minus p minus 1. So the idea here is we get this statistic, we compare it to this distribution, and we will reject the null hypothesis if the statistic is unusual relative to the hypothesized distribution. Okay, so nothing new here. The only thing that's different is I'm not giving you an explicit formula for what the standard error is. Now what we're going to do on the next page is see just a little taste of the power of this multiple linear model or multiple linear regression framework. Okay, here's one example. Suppose you have one covariate, and only one covariate, but you don't think that the relationship between the expected value of the response and the covariate is linear. You think the relationship is curved, and in particular, you think a quadratic relationship. So a parabola would describe the relationship between the expected response and your single covariate. So at first glance, this is going to look like, okay, we can't use the simple linear regression framework because it's not linear. But here's a case where multiple linear regression helps us out. So let's look at the notation here. y1 to yn is the response. x1 to xn is the single covariate. The linear model is the following, b0 plus b1 xi plus epsilon I. But in this particular case, we don't like the linear model because we don't think the relationship between the response and the covariate is linear, and we prefer this quadratic model. yi is b0 plus b1 xi plus b2 xi squared plus error. So, like I said, at first glance, it looks like this doesn't fit into our framework, but it actually does fit into our multiple linear regression framework. So if we just define these two covariates, xi1 is xi, and xi2 is just the square of xi, we can rewrite this model that we like, the quadratic model, as a multiple linear regression model. So we can write this as yi is b0 plus b1 xi1 plus b2 xi2 plus epsilon I. So here xi1 is just this xi, the covariate value itself, the raw value. And xi2 is this value, the square of the covariate. And then, of course, we have the error as well. So even though at first glance it looks like we're out of luck here because the relationship that we like is not linear, it still fits into the multiple linear regression framework because we can write it in the form of the multiple linear regression model. And then, for example, if you wanted to test whether the quadratic model was significantly better than the linear, you could just do a t-test for whether b2 is 0. All right, the next one that we're going to spend a considerable amount of time on is when you have what's called a categorical covariate or a factor. So here's an example where we have the covariate is dog breed, which is not like a number, it's a category. And we have in our data set, we have 3 different dog breeds, Greyhound, Labrador, and Poodle. So the way we're going to express the model is with these indexing functions that we talked about in the first lecture on mathematical notation. So we're looking at the ith dog, and the value of the indexing function is going to be 1 if the ith dog is a greyhound, it's 2 if it's a Labrador, and it's 3 if it's a poodle. So we're taking this sort of categorical covariate and we're turning it into a number, 1, 2, or 3. So for example, if the second dog is a greyhound, J of 2 will be 1. And the model that we like for this particular response, suppose the response is weight. So each dog breed has an average weight, and the weights differ between the 3 breeds. The model that we like is the following. Expected yi is equal to b0 plus b sub ji plus epsilon I. So if we go back to that model, that example I just talked about, where the second dog was a greyhound, you would get y2 equals b0 plus b sub 2 plus epsilon I. So what this means is that the expected value of yi is going to be one of 3 things. It's going to be b0 plus b1, or b0 plus b2, or b0 plus b3, depending on the dog breed associated with the ith response. Now this again, at first glance, does not look like it fits into the multiple linear regression framework. If you look at this formula, there's not even a covariate. It's not like you're writing b sub j times xij. But it turns out that if you're clever about how you define your covariates, you can squeeze this in to the multiple linear regression framework. And the way that's done is with something called dummy variables. So I'm not going to spend a lot of time on this here because we're going to do a whole set of lectures on this. But if you define this variable xi1, this is called a dummy variable for greyhound. It's just equal to 1 if the ith dog is a greyhound and it's 0 otherwise. And then you define similar dummy variables for Labradors and Poodles. You can write down this exact model in this form, which fits into the multiple linear regression framework. So I'm not going to go through the examples. It'd be a good idea for you to say, suppose dog 2 is a greyhound. What do you get from this formula? And verify that it's the same as this one here. Okay, so that's just a little taste of the power of the multiple linear regression framework. You'll notice this set of notes is actually pretty short. It's not actually that complicated to extend the simple linear regression model to the multiple linear regression model in terms of notation. The main difference is that the interpretations of the coefficients it's the effect of changing one variable while holding all the other variables constant. And it's extremely important to remember that distinction.